Okay, let's do a little lesson on partial fractions, and there's going to be two parts to this. Part one, I'm going to take you through kind of two basic examples, and then part two, I'll do some of the more complex ones. I'm going to start though with some algebra, and the best part about partial fractions is that honestly, it's all about algebra, and the calculus piece of this technique is actually really easy. Again, this is going to be a technique that we use to evaluate certain types of integrals. Okay, so let's look at the algebra first. I'm going to have 2 over x minus 3 plus 4 over x plus 1. Let's just take a look at that. All right, I'm going to add fractions, and when I add fractions, I have to multiply top and bottom in order to get a common denominator. Again, hopefully I'm telling you something that you already know. I'll multiply this one by x minus 3 on top and bottom. All right, I now have a common denominator, so I can add those together. So that's 2 x plus 1 plus 4 times x minus 3, all over that same denominator. Hopefully I'm not boring you with some of this algebra, but all I did was take two fractions and I added them together. I'm going to simplify a little bit now. This is going to be 2x plus 2 plus 4x minus 12 all over x minus 3, x plus 1, and let's go one more level down, and that's 2x and 4x make 6x, and a plus 2 and a minus 12 to make a minus 10. And I'm going to go ahead and multiply the denominator out and make it x squared minus 3x plus 1x is going to be a minus 2x minus 3. Okay. So if you made it through the video this far, here's the home run of partial fractions. Partial fractions does this. We are given this integral. Okay? This is a partial fraction problem. It says integrate this function. And you're like, huh. Well, it doesn't look like it's a logarithm. It's not a power rule. It's not a trig function. It's not an exponential. It's not a u substitution. I mean, good luck trying to make that u and then turn that into du. Right? This doesn't fit any of the previous strategies you've used to find an integral. So you don't really know what to do. And the key to partial fraction is it's going to take this and go the opposite direction and find these guys. Remember, the goal of partial fractions, instead of integrating this, it's to integrate those. These are really easy integrals. But if this 2 over x minus 3 plus 4 over x plus 1 is equal to this, well, why would I want to do this integral? Why not do something that's equal and do the easy integral? So the method of partial fractions is decomposing something like this into some linear things. And I say linear because the denominator typically will be linear. On the two examples that I show you in this video, they'll both be linear. So the entire process, and again, I'm going to leave this to you for practice. After you've watched this video, go ahead and write this down and then see if you can integrate it. And again, the whole goal is to turn this into this and then integrate. Okay, but I'll do two other examples because you already kind of know that answer. It's right there. Okay, so example number 1. I'm going to have you integrate 5x plus 7 over x squared plus 3x plus 2 dx. Okay, so let's say that's the original problem and you want to integrate that. Okay, and I'm going to walk you through the process on how to break this down into two pieces and then integrate the pieces. Okay, so the first thing you want to do is that we're going to claim that 5x plus 7, and I'm going to go ahead and factor that. That's probably going to be your first step every single time. I'm going to claim that I can write this as sum a over x plus 2 plus sum b over x plus 1. Okay, and we might have to spend some time to think about why I can make this claim, but I'm going to claim that I can find a and b that makes this plus this equal to this, and the key is for all x. For all x. Right? This is equal to this. I didn't have to assume an x value. Literally, this thing, no matter what x value you put in, is equal to the sum of those two things for every single x value there is. So, and again, there are going to be unique values for a and b. It's not like you're going to do it and you're going to get 2 and 5, and your buddy's going to do it and he's going to get 3 and negative 2. There exists unique a values and b values such that this plus this equals this. And I'll walk you through. The key is that it has to be true for all x. So what we're going to do is we're going to solve this like we'd solve any equation. We're going to multiply by the lowest common denominator. So we're going to multiply both sides of the equation by those two. But if you multiply the left side of the equation by those, well, the denominator just cancels. If you multiply this term by x plus 2, x plus 1, the x plus 2 goes away, and you're left with a times x plus 1. And over here, you multiply this term by the denominator, and you're going to get b times x plus 2. Okay? That's just, multiplying and solving fraction equations, old school algebra 2. But now I have this. And remember, this statement is equivalent to this statement, and this has to be true for all x. So let's just pick an x value. Think about what's the easiest x value to pick if we want to solve this. Well, we might as well pick x equals negative 1, and you're going to see why here in a second. If I look at this, when x is negative 1, this is equal to 2, right? Negative 5 plus 7 is 2, and look what happens. If I put a negative 1 in for x, this is a 0. 0 times a is 0. A negative 1 in for x here just makes this 1 times b, and I get 2 equals b. I'm like, oh, sweet. Look at that. I already know what b is. B has to equal 2. Okay, now think about what's the next x value you want to look at. Again, this has to be true for all x. I don't know, maybe negative 2. Why not? Why not just get rid of that value? So if x was negative 2, this would be negative 3 on the left side. This is going to be negative 1a. And then that's going to go 0. And so you get negative 3 equals negative a, which tells us that a equals to 3. Okay, can you see that? Now I have a and b. And again, I'm just going to make sure you're okay with the fact that I could have picked any x value I want, and this is going to be true. What if I said, you know what, I'm not sure. What if x is 0? If x is 0, this is 7 equals a plus 2b. And I would have got two variables. Might as well pick x values that got rid of one, but look. A, 3 plus 2b is still 7 equals 7. These values work. For this, they'd work for every x value. But if I know b is 2, that means that's really a 2. And a is 3, that means a is a 3. And that means that this function can be rewritten. Instead of integrating this, I can integrate 3 over x plus 2 plus 2 over x plus 1. And that integral is really easy. The integral of 3 over x plus 2 is just 3 natural log of x plus 2. Right? That's just a nice du over u plus 2 over natural log of x plus 1 plus c. Again, both of these are just easy logarithm integrals, 3 natural log, 2 natural log, and boom. If this is the integral of the red, but the red equals the blue, then that's what the actual integral is, and then you have your answer. Right? We've integrated a new type of function by decomposing this function into its linear factors. Okay, I'm gonna do a whole nother example really similar to this. Again, think of the process. You look at this, it doesn't fit any of our current models. We factor the denominator, and again, if the denominator can be factored, it might even be a key that partial fractions is the right technique. I rewrite this as a sum of linear factors. I do algebraic manipulations to figure out what these two numbers have to be. I then put the numbers in, and instead of integrating this, I integrate those two. Okay, I'm going to do one more in the first part. Okay, let's do the integral of 17 minus x all over x squared plus 2x minus 3 dx. Again, you look at that, it's not going to fit any of our models, and so let's rewrite it. So down here, first thing is, right, 17 minus x all over, and let's factor that. X plus 3, x minus 1, and let's claim that we can write this as sum a over x plus 3 plus sum b over x minus 1. And of course, it doesn't matter the order. If I would have switched the order, then I would just switch what coefficient goes where. So it doesn't matter what order you look at. Okay, and then I have to solve this. And again, this is true for all x. I'm going to take this equation, I'm going to multiply by the denominator. I'm going to multiply both sides of the equation by the denominator, which turns that statement into 17 minus x equals a times x minus 1 plus b times x plus 3. So I'm just working with the fraction. Okay, now I'm going to look at specific x values. Hopefully, based on the last one, you have an idea that I'm going to use x equals 1 because it'll make that 0. And if x equals 1, it makes this 16. It makes that 0 and it makes that 4b. But if 16 equals 4b, then b must equal 4. Okay, now I'm going to say, well, what if x is negative 3? If x is negative 3, it's going to make that side of the equation 20. It's going to make this negative 4a. And it's going to make that 0, which tells me that a is negative 5. Okay, again, right up here, that means a was negative 5, and b we know is 4. So this integral is really the integral of negative 5 over x plus 3 plus 4 over x minus 1 dx. And again, those integrals are just logarithms. The integral of negative 5 over x plus 3 is just negative 5 natural log x plus 3 plus 4 natural log x minus 1. And we're done. We took this thing, which are pretty much all these integral techniques are, we took something that we couldn't do and we manipulated it. In this case, this is just the partial fraction, which is an algebraic technique to decompose this thing into two linear factors. And then we can integrate the linear factors because we turned it into something that's pretty easy. And almost all the partial fractions end up with linear factors, such that the integrals then are all nice, easy logarithms. Okay, these are two examples, and again, if you look back at the original one, you can go ahead and practice that on your own. Remember, the original one was the integral of 6x minus 10 over, what was it, x squared minus 2x minus 3, something like that. And then your goal was to integrate that again, so you can look at that and look back at the original thing and figure out that we can do it. Okay, hopefully that's enough practice for at least part 1.